and I would like to make it interactive. So, if you have any questions, just let me know. My name is Rama Karedla, and I work for Intel. Please don't shoot me. I work as a performance architect. My goal is actually focused on the financial services vertical. Can you all hear me well? Okay. So we have a lab in Parsippany, 20 miles from here, that we do lots of fun stuff in with new processors, new NICs, PCI-based SSDs, and of course, the latest and the greatest Haswells and Broadwells and so on. So, what I want to talk today to you about is programming for the Xeon core. So, what does it mean? I mean, a lot of people have grown up with the Xeons, with the Xeon architecture. At the same time, my interactions with customers, I sort of feel that developers know a lot. They know a lot more than I will ever know. But something I realized one thing. I was at a major bank. I wouldn't like to boast, but 90% of the server market is Intel. So we were actually, I was there, and we were doing some optimization work, some software optimization work, and also optimization, especially for low latency, is everything, right? I mean, you folks know that. I'm sure a lot of you are into low latency types of applications. So we did the optimizations, and then the person calls me back and says, I don't see any benefit. So I said, really? Well, we had all these cool features, in this new platform, and then we find out that this gentleman had no idea what machine he was running his code on. And then I realized, I've seen this before also, and I realized, developers, of course, it depends upon the company, your company, where your code has to run. Does it run on the grid? Does it run, next to you in your office? Maybe you don't care about anything but SSE 4.2. I mean, that's the lowest common denominator that you can run. That's what your DevOps guy tells you or your grid person tells you. But I still think that having some idea of the underlying architecture will allow you or allow your application to take full benefit. So this is the premise of my talk today. It's a pretty straightforward talk. Maybe it may be very simple. I've just tried to keep it extremely simple so I can get the basics across. If it's too boring, please let me know, and then I'll try to, talk about other stuff. Here are the disclaimers that I can't even read, but we are required to do that. Okay, so the agenda is we'll go through a brief introduction about what I'm going to talk about. A good portion of this talk is built upon typical questions that I'm asked by developers. So I thought I'll focus on some of them. You may not agree with some of what I say, and that's fine. Let us know. But my focus is the Xeon platform, x86 64. That's what I'm focusing on. So we'll talk about how, there are questions about how do I time my code, some basic questions around that. Then we'll talk about, okay, so here you're a developer, and you want to understand your platform, because I say, it'll be nice. Then let's understand the hardware. So we'll spend a little time understanding the hardware, the BIOS parameters. Some of you folks who are into extreme parallelism or performance would like to know everything, right? What's the latency of this instruction? What's the latency of that instruction? What's this feature? What's that feature? So on. So we'll start at the BIOS. That's an important beginning. And then we'll talk about data access. How do we lay data? Not too much in terms of software, because I'm sure all of the the previous topics must have gone into it a lot. I'm going to talk from the hardware perspective. And then we'll talk about using your cores. Intel, as you know, is coming out with tons of cores, so what are we going to do with it? We are paying for it, so we may as well use it. Oops, sorry. Then we'll talk a little bit about memory ordering. This itself is a huge contentious subject, and what Intel said and what some research papers said and so on. I just want to point out a few things, that's all. Using, and then we'll go on to talking about locks. Typically what type of lock scaling, since we're going to see a lot of cores. So, lock scaling becomes very important, and you really need to pay attention to that besides TSX. Then we'll talk about profiling your code. At this point, I want to say I'm not trying to promote any of Intel's software products, but I'm using it as a base, that's all. Please feel free to use GCC, please feel free to use Perf. I use it myself. But I'm just going to highlight some Intel products because, to be honest, I didn't make the slides for those. Andy Clean was telling me that. I should have done that. Anyway, so we'll talk about NUMA considerations. Now, this is pretty important, and what you can do, what you can't do. Take NUMA into account. References, I don't have any references right now, but when I give the slides, I think they will collect the slides, then I will see to it that you get a lot of references. The way I see this talk is I'm hoping that you take these slides, and instead of Googling on the internet for this, for that, for this, at least you'll find them all in one place, at the very minimum. Okay, so let's talk. Well, I've already said all of this. Coding and optimization go hand in hand. That's very important. I've seen this a lot, really. People put a lot of time into coding, and their deadlines, understandably so. Everybody has deadlines, and then someone says, "Oh man, this thing isn't performant." And then you say, "What do I do now?" So are you going to go back and, it's like taking your pant, then removing it, and then again restitching it. In the meantime, your boss comes and tells you, "Hey buddy, you've got to add this, this, and this also." And then it becomes a major issue. So do you do this, or do you optimize your code? And so if we can go hand in hand, although my slide deck does not have what I'm talking about in terms of optimization as I'm talking about other stuff, but that's the right thing to do. Okay, so timing is everything. Who hasn't heard of RDTSC? Is there anyone who hasn't? Great. So I just want to point out a few things. I'm not trying to educate you on, because there's a lot of stuff. I'm going breadth-wise just to cover more topics. I feel you folks already have the depth, so I'm just trying to cover more topics. And with RDTSC, what I wanted to say is, it is invariant of C states. How many people do not know what C states are? Okay, C states are the state a core can be in. It could be in the C0 state, which is the active state, or it could be anywhere between C0 to C6. We haven't gone to C7 as yet. And succeedingly, the core goes inactive, more inactive. So for example, in the C6 state, it flushes all its caches, shuts down the circuit, because now everything is into power savings, right? So that's the maximum, totally inactive state. C0 is the active state, and you have a couple of mini states in between. So whatever state the core is, the timestamp runs invariant at the frequency that was stamped on it when it was made. So if it's 2.4, it'll run at 2.4. You turbo it, that's fine, but the TSC runs at 2.4. So it's synchronized. This is post Nihilum. So, we are into Ivy Bridge and Haswell's. I don't know if you guys use Haswell's as yet. So the point is, it runs at a constant frequency. It's synchronized across all cores, sockets, as long as you don't need a multi-node controller to, in your IBM or, a HP 12-node box. As long as you stay within the same node, it's synchronized and it's the same. Now this isn't a serializing instruction, so what happens is it doesn't serialize, so if there are any reads or writes, then there is no serialization that happens. But if you run two of them back to back, and I'm hoping you folks are doing that, then you should see no problem when you try to time your code. The question again is, do not use these instructions to time small pieces of code, like 100, 200, 1,000 cycles. The overhead of 30 cycles for each call, plus, these are all out of order machines, right? Does not guarantee you fidelity. So if you are looking at a code sample that's about a few thousand, maybe 5,000, 10,000 cycles, not too much actually, then you will see better accuracy. So that's all I wanted to say in this. Don't worry about, now some people come and ask me, oh, so what do I divide it by? So I take, cycles here, then I have to divide it by the base frequency, right, to get the, to get the time taken. So what do I divide this by? Should I go, I don't know where it is in turbo. I mean, it could be at 2.9, could be at 2.8. So the question, the solution is this. Don't worry about it. Just use the base frequency, because it runs independent of the turbo frequency. Sometimes, now people tell me, no, Ram, this is really not true, especially the low latency guys. I do see a difference. And there is a certain slight, very slight difference in a couple of cycles. But the main problem comes due to jitter, OS level jitter, and any SMIs, system management interrupts, that could be causing stuff, because the OS can't catch them, right? So before you do the write, something could have happened, and then you have thousands of cycles of a difference. So this is, I just wanted to say RDTSC, RDTSCP, a new one, which uses, you could use the L fence with that. Both of these instructions are great for timing. Now let's look at important BIOS parameters. I was just talking about C states. From C0, the most active, to the inactive C6. Now, you can disable C state transitions in inactive states in the BIOS. So you can actually disable C states. Do any of you folks do things like that, disable C states? Okay, cool. Yeah, that's great. You could also offline cores if you want, and that's wonderful. Let's say you've got a 18-core box, and some of these guys do it. I've actually seen them. So I said, why do you need 18 cores? He says, no, I don't need the 18 cores. I need the L3 cache of the 18 cores. So I'm going to offline 5 or 10 cores. I don't care about them, but I want that 45 meg cache, because everyone knows that if you offline a core, you can't offline the cache, that portion of the cache. So, you can offline cores if you wish to. There are people who do options trading and other things, or in-memory databases who love the 18 core. Is Jeff Birnbaum here? Oh, he just left. Okay. So, Turbo is, one other thing is Turbo is opportunistic. So you cannot, so there is a certain amount of variability. It depends upon the amount of power budget that is available to the socket. And so if you say 135 watts TDP means that is the envelope under which it is working. So you are going to get as much as you can until you hit 135 watts. And typically, if it's at 2.6 gigahertz, your turbo could take you up to 3.1 gigahertz with all the cores active. But there is going to be that little bit of variability because turbo is opportunistic. Turbo, you can, with D-pad technology like Dell has, or with turbo limit MSRs, you can keep it at 3 if you wish, or 3.1. But you cannot prevent downward transitions. I just, for all you low latency folks, I want to make this very clear that you can cap it, but the processor being what it is, a few downward transitions at times will happen. How is it going to go down from 3 to 2.6? No. Around that from 3 to 2.95, 2.96, but around that part. But there are some downward transitions that cannot be helped. So the new version, now previously we used to have all cores, like in Ivy Bridge, you turn turbo on, all the cores get turboed. So that is kind of wasteful if not all threads are important to you. So in Haswell, the new one is there is actually a power management algorithm that looks around, it operates once every millisecond and looks around, says who is busy, and divert power and voltage to that particular core to boost that. And the others which aren't that busy, they don't get boosted down, but they remain the same. So any extra power there is given to that one core. One of the things we've done in Haswell is to decouple the core and the on-core. What is the on-core? The on-core is the L3 cache, the memory controllers, all of that stuff. Why did we do it? Because we wanted to save power. So if you're really not computing, then you are somewhere in the, there is memory latency going on, you're accessing the memory, the L3 cache, move power here. But if you really need power for compute, then you take power from here. All of this has some implication for variability, for those people who don't want all of this. But still, we have a lot of architectural benefits which overcome these situations. Hyperthreading, it's great. Do you folks use hyperthreading? I'm just curious, how many people actually use hyperthreading and turbo? Wow, that's it? That's it? Man, we aren't doing a great job then. I got to go back to the architects and tell them that. Can I ask why? Can anyone say, there are various reasons. People will say, my grid guy said, hey, I can't do it just for a few. If I have to do it, I have to do it for everyone. I'm not going to enable HT for all of them. I'm not sure. Performance could degrade. There are many reasons. We're just trying to understand, or you can talk to me afterwards, or you could send me an email. We would be very happy. The architect sitting in the factory in Oregon would be very happy to hear these reasons. We do put in a lot of money and effort into these features, so, maybe we aren't doing a good job with educating people also. For example, AVX2, AVX. So that's my role at this point. Okay, so enabling DDIO, as you all know, puts NIC traffic as well as PCI-based traffic, all PCI-based traffic, directly into the L3 cache of that particular socket that the PCI slot is connected to. Please don't disable that. Keep it on. And if you have NICs like Solarflare, Mellanox, you don't have to buy Intels for, we don't compete in the low latency market here. So, but we do for virtualization as well as throughput. We do an excellent job there. So enable DDIO and let Solarflare or Mellanox or any other NIC make use of this. As I said, the encore frequency, you can keep it coupled. It is uncoupled from the core frequency, but you can keep it steady at one max limit that you desire, so it doesn't keep fluctuating every time power moves from the core to the encore. These are some typical numbers for how much turbo you can get. So let's just take the 18 core, which is the 2699. It's got a great 45 meg cache per socket. And if you were to use only one core, which is highly unrealistic, you can go up to 3.6 from 2.3. So this is something that tells you how much of a turbo budget you have and how many cores you may wish to offline if you need to. Any questions so far? I just wanted to talk about some new mode. Snooping is actually finding out on the QPI. We have more Snoop modes that we put into Haswell. We have the home Snoop, we have caching agent. Unfortunately, there isn't that much time to, this really begs, we can spend a good amount of time with the new Snoops we've come out. Why have we done that? That is to give you more latitude in trying to decide if you're NUMA enabled, if you're NUMA, if you are looking for more bandwidth, you're looking for more local bandwidth, more remote bandwidth. See, we give the QPI certain credits, and we say, okay, at this point in certain modes, we'll give local memory bandwidth more credits, remote less. In some cases, we'll just equal it. So local and remote latencies and bandwidth are approximately the same. So I just wanted to focus on one. Early Snoop in your BIOS should be set to, I suggest you enable early Snoop. It gives you the lowest latency and decent memory bandwidth. There is another one called cluster on die, and this is what we introduced in Haswell. What we do is we take one socket and we break it. So here you see, this is for 18 cores. So we have 4 and 4 and 4, 12, and then we have 6 out here. So we broke, we took 8, and then we broke it up this way. We made one cluster out of it, and then we took the rest and made that a cluster. And then each one gets its own home agent, which is and a memory controller. And since this one has a 45 meg cache, we actually divide the cache also to both these partitions. Why do we do that? Because we believe that if you had all your threads running, very segregated. So let's say you have 9 threads on this, and you're doing something, you're doing some sort of a Monte Carlo options or binomial, and so there is nothing to do with the remaining 9, the other 9 threads. So this way, what happens is you save on Snoop traffic, and you get very good memory bandwidth. So I remember Jeff telling me that he got about a 30% gain just from cluster on die, which is fantastic. But then he had a great application too. he knew just how to tweak the thing. Uh, so here is some fun stuff. We call it cache monitoring technology that we have started with Haswell. It monitors your L3 cache. And what it does, there isn't that much time to go through. Essentially, just in a couple of lines, we have cache monitoring technology and cache allocation technology. Cache monitoring monitors your cache is a 20-way cache, right? So that 20 ways. And I should have put the earlier slide first. Anyway, so as many cores as there are, let's say there are 18 cores here, you'll have 18 slices of the cache. And then what happens is the slices have no correlation to the core. Okay, we depict it as if there is a slice here, there is a core here. I'll show you the diagram. It does not mean that this core's data is next to it. Would have been great, but then you end up creating hotspots, right? If something like that happens, we don't want that. Our algorithm takes the data before putting it into cache, hashes it uniformly in all of the cache slices, and places it. So you can try to defeat it. I really don't think in the long run it helps, because we do a great job of hashing it and distributing it all over. There are some people who will tell you, no, if I put it on this core, I get a couple of cycles less. Perhaps. So this technology that we have in Haswell will monitor your L3 cache at this point. So if you have a situation where you feel some thread is very noisy and is impacting the other threads in the L3 cache, you could do something about it. There's not too much you can do with just monitoring, right, unless you can take action. On some SKUs, we enabled allocation, where you could actually go and you can change things. Like, let's say it's a noisy VM. You take it and you move it somewhere else. It's a thread that's getting a lot of market data and it's thrashing the cache. Okay, so you could increase the size and say, instead of 4 ways or 2 ways that you currently have, take 5 and be happy with it. Don't thrash other people's lines out. Don't evict them. What happened? Shoot. Oh, sorry, this. Let me just do it this way. Sorry about that, folks. I don't know what. I think my laptop's taken an earlier vacation than me. Decided to Concord at 5 o'clock. What's happening?
Is the software still there?
Yeah, I tried to, and it just seems stuck for some reason. It's moving, but
Yeah. Can I change the mode to when it's all
sure.
the same, so you
Yeah.
would lose your notes? Let's see if that works.
Oh yeah, that's fine.
We have to open.
Oh no,
the,
we can shut it down and reopen.
reopen the.
Yeah, that's fine.
Which one is it?
Program, yeah, that's the one.
just open the only one presentation.
Sure.
What's the title of the?
Programming, P. Oh yeah, there it is.
Let's see. You were here?
Yeah, that was this. Thank you so much. Thank you. So this is one example of cache allocation technology where you could actually decrease the latency, that spikes that you're getting, which actually are here in red. And with this cache allocation technology, you're able to actually bring this down tremendously. So this is one of the things. This was actually used, this came in for the telco guys, and they were doing it for DPDK packet processing, and then I said, aha, we could use this in the financial services. The financial services and other people are the, are like the canary in the mine, right? I mean, they see anything great, they'll grab it. So, so the point is to, get this to a low latency, and other people who are into virtualization, SDI, so on. So this is how it typically looks. When you monitor it, you have to set up allocations on a core basis. That's how it works. So we make the assumption that you have pinned your threads to a core, and you haven't oversubscribed. So typically on the right-hand side right here, it shows you how many kilobytes each core was given. Now I've truncated it. So this is the occupancy. I have put a reference below, so you can always go there and read more about it. So data access and data parallelism. This is the slide. Apologize, folks. I should have put this up front. This is typically what a cache looks like. You have the QPI links coming from the top. You have the PCI lanes, 40 of them for Haswell. And then you have the cores out here. The cores talking to, there is something called a CBO, cache box, and then you have your last level, your slice of the last level cache, which is typically 2.5 megabytes. Okay, so now since we are increasing so many cores, those days of all of them being on one ring are gone, right? I mean, it's just getting the latency has gone up. So we divided this into two parts, 9 and 9, and then they talk to each other through these switches, these bidirectional switches. And so it becomes, it's a 4-cycle switch. So it takes 4 cycles for something from this QPI to get to this one, to get to the other socket, to get to the other 9 cores. This is still on the same socket. And then here, data goes bidirectionally to the memory controllers. So a little more detail about the bidirectional rings are still 32 bytes in each direction, and core accesses to the local don't get on the ring. So as you know, L1 cache, L2 cache, L1 cache is 32K, L2 cache is 256K. That's inclusive. This one is instruction and data. L3 cache is approximately 2.5 megabytes per core, depending upon which SKU you buy. Typically 2.5, some of them are even more. The cache line size in all of these 3 levels is 64 bytes. A cache line is that. The point I'm trying to make here is, if you want better performance, try and put your data. Obviously L2, it will come down to the L1 cache, which has a latency of 4 to 6 cycles. The latency of an L2 cache is about 11 cycles, and then the L3 cache is about 30 cycles, and then of course you have your memory, which is a lot more. So try to fit the data into the L2 cache. How are you going to do it if you have a huge array? Well, there are various ways you can do it. people talk about cache blocking. You guys are all great programmers. Do you think cache blocking helps? Have you seen any benefit from cache blocking as such? Or the main thing that what I have seen through examining so much of code over the years is the fact that data alignment is important. Even though some of our newer processes can deal with unaligned data, we still see a better benefit when data is aligned. Why? Two reasons. First thing is you don't have to do a gather. Gather, we now have a gather instruction in Haswell, which means you have data all around, and then a gather has to, it just can't go gathering everywhere. There is an index stride to it. So it has to do that. So if you align it, you help the compiler too. And this is the data access. You can do memory transformations. Typically what we found is for good performance, if you have an array of structures, which most people typically do, we try to, the way data is handled, it's better in memory if it is converted to a structure of arrays, because then they become more contiguous, and then you can, your access, you can use the memory bandwidth very well. Otherwise, in the array of structures, it becomes very disjointed, and then you have to start calling your gather operations. By the way, I'm focused only on the Xeon server. Sammy said focus on this. I'm not talking about the Xeon Phi or anything else. That has a slightly different architecture. So the point is to do the memory transformations as well as the data transformations. Now, in terms of, some people like to do prefetching. What we have seen is, I'm not sure, I mean software prefetching. I don't think software prefetching really, with hardware prefetching, I don't think it's really beneficial, and it could even hurt you. The hardware prefetches are great. The new ones actually cross 4K page boundaries too and go on. And they see a pattern, and then they automatically start prefetching. So there really is no need for you to also initiate a software prefetch. If you want, use your compiler, your favorite compiler, GCC, ICC, Windows, and try to experiment with the prefetch distance, right? Compiler is king. Compiler should be king. I'm not asking any of you to write stuff in intrinsics or assembly. You should not have to, unless you're a low latency hedge fund or somebody. So compilers should do the stuff for you. And we are working very hard to do the vectorization for you, to do the the prefetch, to do the gathers, everything. And we are definitely putting the bits into GCC. So the bits that you will see eventually will go into GCC, because we support GCC also, although we don't make any money off it. But that's our commitment to Linux, open source. So at this point in time with 4.9, we still do a better job of vectorization, but we really want to see GCC catch up. So our bits have to get in there. And they do. Sometimes it takes a little time. So the point is this, the takeaway from here is leave the hardware prefetchers enabled. They do a fantastic job. Try not to do software prefetching in between, unless and until you've seen some fantastic benefit. And leave it to the compiler. Pretty smart compilers now, GCC, ICC. They're getting better. Let me quickly talk about vectorization. Actually, I think Uli covered this stuff, right? So it's essentially doing, working with data in parallel. So for example, as you see this loop out here. So that's the point. The point I'm trying to make is you guys have paid money for those cores. You guys have paid money for the vector units. So please use them. Get your money's worth. That's the point. I know a lot of people are still at SSE 4.2. Some of them may even be single-threaded, multi-process. I totally understand. I see it every day. I cover all the major banks and everyone. The reasons to not move, I understand, but you're leaving performance on the table. Now, some of them are very scared. You have 20-year-old libraries, and you're not just going to go and say, okay, I'm just going to go to GCC 4.9. It's kind of hard, and we understand. But still, the point is we want to work with you. If you have code that you think you want to optimize and you think, hey, you know what, I think I can vectorize this, that'll be wonderful. Get in touch with me and we can work with you. I remember one, and this is something I like to talk to you about, is there was a person at a major bank. He was working on mortgages, fixed income bonds, and so on. And then, I worked with him. God, we worked for 2 years. And the amount of stuff, bureaucracy or anything, or the chances to actually take that code and do something serious with it. Because he said, if I do a full-scale thing, they'll go through an audit, and which will last 9 months. Because you have to verify, right, that the numbers you are getting with your new code are as good as the old code. He said, forget it. Then, for some reason, he had to leave, the company, and then he started his own company, and he had, similar idea. This was his brainchild, his baby. He started, and now he started bottom up with vectorization. He had code that he could start and say, I'm going to now start bottom up, and I'm going to design it the way I want, the way I think it is going to be really, it will vectorize. He came from a Cray background. He understood everything, but people have there are lots of constraints we all have. So the point is, don't leave performance on the table if you can. If you can't, do it in parts. So how do you write code to use the vector units? Well, use the compiler's flags, use Pragma, use the Intel Silk Plus array notations. They're pretty good. And very simple, elemental functions can be used. Use Silk for parallelism. TBB, they have the same runtime scheduler. And so this is simple ways to write it. I won't talk about vectorization. Fuse, multiply, add is the new instruction we put into Haswell, and gives you much lower latency. You can do 3 things in one. Well, I don't want you to use fuse, multiply, add, go and put an instruction there, leave it to the compiler. I'm just telling you about it. So this is the power of data and thread parallelism. Use your cores, use your data. Look at this Monte Carlo simulation, right from Ivy Bridge 12 core to a Haswell, just in 2 generations, that's it, right? Ivy Bridge to Haswell. We were able to get a 3.13 speed up. Both are AVX, but just due to cores as well as AVX2. That's what we put into Haswell. Is there a concern about using AVX in terms of the power that it is drawing, and there's a concern that you may lose performance? I've heard this through some people that we are concerned about it, but you don't have to be. Even though AVX registers are 256 bits, they draw more power than typical SSE registers. You still see a much better benefit because of the wider registers. This is typically, so I've taken real workloads, real production workloads, and looked at the amount of difference. There's very little. Forget the thing on the left. It's just a transient. But if you see, it's between 2.55 and 2.6 gigahertz. That's the drop when you use AVX constantly. So should you be concerned? No. Not all AVX instructions draw the same amount of power. Some do more, some do less. Okay. this is one library I would like to recommend. Now, this library I would like to recommend because these guys have really worked hard and done a lot of optimizations. Whether you're talking about BLAS, you're talking about LAPAC, this is they've really gone and done stuff in assembly and all of that stuff. So these guys are really good. Do test it out. It comes free with the compiler. If you don't care for the compiler, at least link to this library. Okay, codes and threads. I believe we covered this: data alignment, array of structures to structure of arrays, cache aligned memory blocks, vector loops, and Uli must have done a great job here in any case. So the trend is towards more cores and thread parallelism with data parallelism. You paid for it, go ahead and use it. Under subscription and over subscription are two issues I keep seeing all the time, and that really cannot be helped. Some people like to oversubscribe because you don't have to pay the grid that amount of money because you're paying the grid on a per core basis. So if you can oversubscribe and you pay for 10 cores and you put 15 threads on it, you saved on 5 cores. But besides that, oversubscription to a certain extent does work in some cases. In some cases it doesn't. Latency sensitive applications will use the cores in a different way. Each core will do something, each thread they spawn off and then they do their own thing. If you take some sort of an options pricing type of app or risk analytics, well, they all work on a certain amount with data that each thread cuts and munges that, and then they put the result back together. Thread parallelism here works extremely well. One of the things, as you increase the number of threads, is the fact that you get into lock problems. Here you have threads, unless you have lockless, which is kind of hard. You have lock contention, which scales, and you can use VTune because VTune's pretty graphic about this, and you can see where you are actually waiting, where you're spinning, and what you can do about it. It'll correlate that to your source code. I'll go through this quickly, and this is actually using simple pragma OMP, which GCC 4.9 also is supporting right now, right, Sammy? I think 4.9 supports GCC. Supports pragma OpenMP.
I don't use OpenMP.
Okay. So, well, pragma SIMD is a great pragma which you can use for vectorizing your code. Very simple statements. And let's talk about Silk Plus very quickly. By using simple Silk spawn, Silk for, you can get some good, parallelization benefits. Please do use vector reports as well as optimization reports from your compiler, be it ICC or GCC. They tell you a lot. For example, they'll tell you where things are optimized, where some loops are not vectorized. Intel Inspector is a great tool if you want to look at memory leaks and try to control your memory pressures, memory growth. Let's quickly go to memory ordering and locks, memory ordering lock scaling. Just one point that I wanted to make in memory ordering is something that was not clear is the fact that 2 stores would be seen to be ordered by, let's say you have 5 processors, 5 cores or 10 cores, and then 2 of them are actually in an exchange are in the process of loading. Well, to these 2 processors, they can see that the actual values, but as far as the rest of the process are concerned, they would see a very consistent they are seen to be ordered. So that is something that we did not put, and then there was this research paper that essentially said the same thing. So I think we sort of concur with what the research paper said. Although the architect isn't going to say that, but. So as the number of cores increase, contention becomes an issue. I have a huge paper that I wrote some time back on lock scaling, lock analysis with Andy Clean. The point that we have realized is you can't keep polling constantly. If everybody polls everybody, what is going to happen is performance is going to degrade because the ownership of the cache line keeps changing all the time. So to say it in one line, the point is avoid short re-entry, spending very little time in the critical section, and in between. Try to keep it at about several hundred nanoseconds. And then see, Westmere and all, they were slower. So if you had 10 threads, one thread could actually spend enough time and do all the updates. And that was unfair. So as we went to more cores, we decided, this isn't going to work if we let one core, one thread take away with all of this. So we decided to become fair. So we quickly pass ownership back. So the guy who has it has to relinquish it, and it looks like it's a degradation, but it isn't. It's actually fairness across all cores. So Intel's TSX architecture, unfortunately, was disabled due to some very minor thing, but we took the thing to disable it. What it does is, in such situations, it takes the coarse-grained lock and converts it to a fine-grained lock. And then places the data in the L1 cache and elides it. If there is contention, then it rolls back, and then it'll try again. So I can't tell you too much about it until we get some. We got some excellent work with SAP on this. We got some great results, also with other companies, but I think the proof of the pudding is when it comes to you guys. So this is a simple VTune example. I'm sorry.
Sorry, any update on when the TSX functionality is coming back?
Yeah, it should be available in Broadwell server, but we are also coming up with Haswell EX in 2 months, 3 months. So you should see it in Haswell EX. This is typically all the threads out here, and you can see how all the threads are communicating through these yellow lines. It's kind of busy. I wish I had done a better job. This shows the spin time. I blocked it out because this is actually a real-world banking app. So I blocked out the functions, but just to show you, this is a real-world app. Code profiling. Well, this is VTune. As I said, we don't make money on software. We make money on our processors. So, but still, we do a great job with our software. We do a fantastic job. So I'm not trying to push. I'm just trying to show this as an example. But we do a great job, actually. At least we think we do. So here's a function call stack. Let's say you have your source code. You run it. You run VTune on your binary with objects. You can actually choose the grouping as you want by thread, by core. Thread, core, socket, core, thread, function, call stack. So you have the call stack, and this tells you what your CPU time is, your CPU spin times, if there are any. This will tell you the spin and overhead time, as you can see here, the time it's running, the CPU time taken, and if it's blocked, it'll tell you. If it is waiting, it'll tell you. So things like that. It gives you a nice, picture of all your threads. This is another thing. And here, look here. It'll actually, when you click there on the thread, it'll take you back to the source. So you could actually look at the source and see what is happening. Are there any branch mispredictions? Are there any, branch clears? Are there any, fault sharing that's going on? So on. I wanted to spend time on showing you how to profile your code, but it isn't going to be, there isn't enough time for that. So I'm avoiding that. I really want to show you real-world examples with profiling, because I believe through the years that I have seen, people have just gone and coded everything, and then, whoops, performance was a later thought, and then they got bit by it. So working with NUMA, again, as you can see, you have these, this actually does not show, this is, yeah. 2600, okay, so these are 2 sockets, okay, fine. So, as you know, you have some cores on socket 1, some cores on socket 2. And the best way to do that is to try to keep them on the same socket, which is, you know, a lot of people are very NUMA sensitive and smart about it, NUMA savvy. You can do it through core pinning, scheduling, NUMA CTL, or through Windows functions. One of the things, how are you going to find out if you're having NUMA issues? And it's very interesting that it's not difficult. You will see a general slowdown, and if you use perf counters, you can use perf counters. You can look at remote accesses that are made to the remote DRAM. So let's say you are on one socket, and then you see lots of remote accesses made to the other DRAM, and you're saying, why is that happening? That shouldn't be happening. Oh, then someone has migrated there. So that's one way to do it. I'll give you a simple example. We moved from Westmere to Sandy Bridge, where we had the PCI slot connected to a socket now, right? We took away the main PCH. So each PCI slot is either connected here or here, which wasn't the case in Westmere. So then what happened is, all of a sudden, I started getting calls, and the developer, you know, the infrastructure people told this guy, your app is not performing, it has degraded, and he didn't understand what was happening. Well, what had happened is the data, market data coming in through that NIC, they had one NIC, and that was a quad socket, which is taking care of both, you know, threads respond on both. And this one, in this case, they didn't know that they needed 2 NICs at this point to feed both. So one was feeding all of them. So the second socket was actually making remote accesses to memory in the first socket. So things like this you can actually look at, and you know, you could actually correct those things. In some cases, you may want to go UMA, and UMA helps you in some cases depending on your workload. You will have to just try it and, you know, interleave it and see if that helps you, because when you interleave, what happens? Your alternate cache lines belong to different memories, right? So this is it for today. There is a lot I can talk about, but do you have any questions, anything that you'd like to comment on or suggest? I guess you're all tired, huh?
Cool. Well, thank you.
Thanks, Amy.